So, we have been discussing about disturbance growth in shear layers, and we had generally classified the problem into two aspects, that for the sake of mathematical simplification, that the growth is either in space or in time. And there were some examples given. So, we have been looking at disturbance growth either as a spatial problem or as a temporal problem. And one of the examples that attracted us most was this external flow, where we saw through lots of tests and trials that there are situations in external flows where you do indeed see disturbance growth in space. Now, that explained most of the time, like I explained to you about the paper by Trefethan and his co-authors, who pointed out that for shear driven flow it looks okay. But even then it was said that Blasius boundary layer was not a very good example where spatial growth was seen. So, people did talk about from this classical approach, where we either look at spatial or temporal growth. There was this other part where we did talk about the bypass route. Classical and bypass route. In bypass route, of course, we accepted that things can happen simultaneously in space and time. However, in those cases where you do indeed see spatial growth, you also see at times that there are simultaneous transient energy growth. While this transient energy growth was projected as one of the most viable route of bypass transition, what we started discussing before the break is that even when we have strictly spatially defined problem, we do see associated transient growth. And this following part, we are basically talking about a spatiotemporal growth, which is observed directly via linearized receptivity analysis of Navier-Stokes equation. And this is not something new, which we have done for quite some time. The only difference between what we studied here and the rest of the studies in the context of spatial growth is we treated the problem as a fully time dependent problem. Okay. So, we introduced what is called as the Bromwich contour integral. And in this Bromwich contour integral, we approach the problem in the same way as people have been doing, using Orr-Sommerfeld equation, but with the difference that we have to take the contours simultaneously in both the wave number and circular frequency plane. This has been followed up in recent times also, and a very special property of the shear layer was noted, that when you do indeed perform a full time dependent receptivity analysis rather than the spatial stability analysis, you do see that there are multiple modes, there are more than one modes, while the spatial stability theory focuses upon only the dominant least stable mode, but in this approach, in Bromwich contour approach, you do track the presence of multiple modes. And what was noted, this curious observation that we are talking about, that this multiple modes at the onset time of the problem itself can give rise to transient growth, which will grow in space and time together. And this is what we had started discussing about. Well, when you do have some such thing happening, multiple modes interacting with each other, then you start questioning the validity of normal mode analysis, because in normal mode analysis you only study one mode at a time without any recourse to having various modes interacting. When you have multiple modes interacting, then of course Bromwich contour integral becomes a very natural choice. And the most interesting aspect of this is that the results that you obtain is not restricted to only 2-dimensional flow or 3-dimensional flow. If you recall the earlier work on transient growth by various group who talked about non-normal modes, they showed such a mechanism only for 3-dimensional flow. So, let us try to see if we could explore this in the context of 2-dimensional disturbance field itself, and then we can notice this. Now, we do actually adopt the transient energy growth route starting from what we have developed in describing bypass transition in terms of disturbance energy equation that I have written it down for your reference, which we had done in the previous set of lectures, which showed that if I define the energy itself as like a Bernoulli's head that we have talked about before, then I can split this energy into two parts, the mean part as well as the disturbance part. And here we are talking about the disturbance energy. So, if I split this into a mean part and a disturbance part, then we did show the governing equation for disturbance energy is given by this equation. It is basically a sort of a boundary value problem, because energy is given by the Laplacian operator, which is shown here to arise from various interactions of the mean and disturbance field. Subscript m refers to the mean field, d refers to the disturbance field, and some of the terms are of the lower order, for example, this one and this one. So, even if we throw them away, what we notice that the evolution of disturbance energy is given by how mean and disturbance vorticity interact with each other, how basically the mean flow interacts with the helicity of the flow, that is the curl of the vorticity field, right. Also a similar complementary term which tells you how the disturbance velocity sort of takes a dot product with the helicity of the mean flow. What is the mean flow? What we are studying? We are studying a very simple problem here. We are studying the prototypical flow that has dominated this field that we are talking about, say 0 pressure gradient boundary layer, which was originally studied by Blasius. And if we neglect this part where significant growth of the shear layer takes place, then we can treat this boundary layer to be almost like parallel without any growth. And for such a boundary layer, I could talk about a mean velocity profile, which I am calling as Vm, and that is given by this. This is your parallel flow assumption, right. So, this is your parallel flow assumption. That is what we are in a sense saying, the shear layer does not grow with x very much. And then we substituted that in linearized vorticity transport equation to get the azimuth field equation that we know. That was the part that defines this disturbance field amplitude, because this is governed by our azimuth field equation. Okay. Now, what we are actually attempting to do here is to show that the viscous instability theory as given by the azimuth field equation and as given by this disturbance energy equation are equivalent. That is one of the things that we want to show, simply for the reason it is a kind of a sense of completion that I am discussing this with you, because this equation that we have written here is a product of the full Navier-Stokes equation. We did not have to do any approximation, any assumption, unlike azimuth field equation. Azimuth field equation is a restrictive set of equation, because it assumes the flow to be parallel, right, and it also of course neglects all the nonlinearity, whereas this equation, disturbance energy equation that we have developed, we do keep the scope for including the nonlinear term, which has been underlined here. We can keep them, or we can study the linearized part. But then if I am looking at the linearized part of this disturbance energy equation, that must have all the seeds of the field equation, and that is what we are talking about. Okay. Now, there are this historic legacy of studying energy propagation equation for flow instability. There were a couple of earlier attempts by Reynolds and Orr, who studied the kinetic energy only, whereas we are talking about here not only the kinetic energy, but the pressure head too, and in the absence of any other body force, this constitutes the total mechanical energy. So, this is somewhat more inclusive than what was attempted there. Well, it was been discredited later in these following work, where they said that of course, the results that you get out of such analysis, the critical values of let us say the Reynolds number, etc., they are indeed very, very low. So, what you do is you start off with the momentum equation and take a dot product with the velocity field to get this equation, and this form the basis of Reynolds or energy equation. So, we did see that it has a time rate of kinetic energy here, right. What is this? This shows how the Reynolds stress interacts with the mean shear. This is the viscous dissipation term, and this is the gradient transport, because it is written as a sort of del del x j of a term. So, this was the starting point of the equation. There is nothing wrong up to here, but subsequently what people did, they did study this with the assumption that if you are looking at any disturbance field, it is either very localized or spatially periodic, and then what happens is then those gradient transport term drops out. So, the gradient transport term drops out, leaving you with this equation, okay. And these are those dissipation sort of balancing your interaction of the Reynolds stress with the mean shear. Okay, but you realize that this is in a sense, if you are looking at the energy equation for the disturbance, then this quantity, the mean quantity, mean shear is already known. So, what you are looking at is a kind of a equivalent linearized version, because this is a second order tensor, so is E v. that is also a tensor, right. So, in terms of the second order moment, this is a linear equation, and what has happened in making that assumption that the disturbance field is localized or spatially periodic, we have actually thrown the nonlinear term, the inertial term. And this was pointed out by Lin and Stewart, and they said that of course, the critical Reynolds number obtained for many of the flows were too low, and of course, that was tracked to elimination of nonlinear terms that we lost when we made that localized or periodic assumption. However, in contrast, if we look at the disturbance mechanical energy concept that we have written there, the nonlinear terms are very much there, right. You can see the nonlinear terms can be kept if we want to. However, even these terms also originate from the nonlinear convection terms. So, they do not simply go away. Okay. So, the nonlinear contributions are kept intact in this instability study, and this energy based receptivity analysis is all inclusive because it is based on full Navier-Stokes equation. Now, let us spend a little time in understanding how we go about it. Well, how we go about it is the following. We define the disturbance field in terms of a disturbance stream function with a Fourier Laplace amplitude, and please understand that psi d, I have written it as a vector, because if I have a flow in the xy plane, psi is in the k plane. So, that is what we have done, because with the help of such a vector notation of psi d, I could obtain the disturbance velocity. Disturbance velocity is nothing but the curl of psi d. So, that is what we do. And then having described the mean flow and the disturbance flow, we can take a curl of this velocity fields and get the vorticity component. So, we can perhaps get everything in there. Now, if I am looking at the Blasius boundary layer problem with a parallel mean flow assumption, then in terms of those wall modes, phi 1 and phi 3 are the wall modes, because they are the ones those decay with the height. That means, if I excite the flow inside the shear layer, this disturbance stream function can also be written down like this, and you can identify very clearly the dispersion relation appearing in the denominator, right. And this is the type of input, the excitation field that we give. We have talked about various kinds of possibilities, and we can talk about a sort of a impulsive excitation, as we have done for impulse response, or we could take a strip excitation, we could take Gaussian excitation, all kinds of things have been discussed. And these equations have to be solved subject to the various boundary conditions, and in this case, please do understand that we are interested in space time dependence. So, we cannot just simply take the signal flow route, signal problem route, where we just simply say that the time dependence is as given by the imposed harmonic excitation, but we do need to start the problem at a fixed time. Okay. So, basically that is where this Heaviside function u of t comes into picture. That tells you that this problem was started at a finite time. Okay. So, we basically solve this problem. We have this Blasius profile, the mean flow like this, and let us say we position the exciter at a location like this, and so we consider as if this actual shear layer is replaced by an equivalent parallel shear layer with the same thickness at the location of the exciter, and then we study. This is interesting because without this framework for a parallel flow, we do not have wherewithal to prescribe the origin, right. Now, we can even prescribe a x origin for the flow at the location of the exciter. We can also start to give a meaning of what t equal to 0 means. T equal to 0 means when we start the experiment, when we start the excitation. That is how we got that Heaviside function coming through the boundary condition. And then the governing equation can be simplified. This is quite well known. Now, what we do is try to understand this problem, the dynamics via this Bromwich contour integral, by taking various points, and this is what we did. We took 4 points for various reasons. We will see why we have chosen these 4 points. Well, we first of all we wanted to keep the Reynolds number constant, and along this r equal to 1000 point we have chosen 3 points. The point A corresponds to where we expect the leading mode, the Tollman-Schlichting mode, to be unstable. That is what the point A represents. In addition to this Tollman-Schlichting mode, we will have additional stable modes. The point B actually corresponds to one such case where we do not have an unstable quantity. So, this is on the higher frequency side. If this was A was for 0.1, this is 0.15, and here if we do a sort of a stability analysis by grid search method, we will find out the various modes to be stable. In contrast, we are looking at the point D, which is also spatially stable, but which is very close to the neutral curve. So, here if I create an excitation corresponding to this parameter, I am going to see a disturbance field which is hardly decaying. Finally, this point C, which is far upstream of the neutral lobe, corresponds to a case where the Orson field equation does not predict any instability at all for any frequency. So, these are the 4 points that we had studied, and the Bromwich contour I explained to you the last class also, that theoretically speaking in the alpha plane you would like to take it from -infinity to +infinity, and because we are looking at the asymptotic part of the solution for which alpha would be very small. So, these values like plus minus 20 along the real axis. Okay, so, we take 4 representative points. A is the unstable Ts wave point. So, one of the mode is decidedly unstable, whereas B represents a point where all the modes are stable and they are away from the neutral curve. So, the decay rate will be significant. In contrast, point D is also unstable, stable point, but it stays very close to the neutral curve. So, you may see the resultant disturbance field may have a sustained signature of disturbance. Finally, point C corresponds to the case where it is significantly ahead of the neutral loop, implying that here all the frequencies are stable. Okay. And we did talk about in the last class also that we have to choose a Bromwich contour for any point. We will have to choose the point in such a way that all the downstream propagating modes should be above this Bromwich contour in alpha plane. So, that is what we did. We chose a Bromwich contour which is 0.009 below the real axis, and it extended from -20 to +20 in the direction parallel to the alpha r axis. Okay. So, that was your alpha Bromwich contour. Similarly, the omega Bromwich contour, we have to take it, it should be placed so far above, so that any mode that are there, they must be below, because you know that this is coming with a minus sign here. So, all the modes have to be causal. So, we cannot have causality violated. That is why we do indeed place the Bromwich contour in the omega plane at a height significantly higher compared to what we took in the alpha plane. So, this is at 0.02, and here we have once again taken a range of -1 to +1. Whereas, for other points the Bromwich contour in the alpha plane remains more or less same. We could actually bring it closer to the alpha r axis, because we know that unstable mode is not there. So, we can bring it closer to the alpha r axis, and the omega axis we remain the same. So, there is no such change for the omega contour. Now, This will perhaps give you an idea of what kind of effort is needed even in solving a linearized Navier-Stokes equation with adequate accuracy. For example, in the alpha plane, we have taken 2 to the power 14 terms. So, that is 2 to the power 13, 8,192 equidistant point in the alpha plane, and we had taken 512 points in the omega plane, and this was what we did in the 2006 work. And you understand that in the shear layer itself, we have gone only about 7 delta star. We have gone a distance from the wall to 7 delta star, and we had taken 2,400 points for the isomorphic equation. And because we have used a Runge-Kutta method, so we had to take the mean flow, which should be having twice the number of points. So, a Blasius boundary layer with 4,800 points have been obtained. So, this is the kind of effort that is needed, and if we perform a stability analysis, purely spatial stability analysis, then we get the properties of this 4 points as indicated here. As I mentioned to you, the point A was inside the neutral loop. So, it has a unstable mode. You can see it from this sign minus 0.007 289, and that would also tell you why we chose the Bromwich contour in the alpha plane. That was at minus 0.009, right. We wanted to keep this mode above the Bromwich contour. That is what we had done. The corresponding alpha r is given here. It is about 0.279. So, as these are given in terms of delta star, you can see what kind of wavelength we are talking about. It is of the order of tens of delta star. Now, the other 2 modes that you get from the spatial analysis, A2 and A3, they are stable, and you can see the growth or decay exponent is significantly high. So, if this is minus 0.007, it is plus 0.1. So, it is almost like 14 times, 15 times higher, and this is even higher. Okay. The wavelengths are almost like half of it, wave numbers are half of it. So, wavelengths are double. So, these are much more longer waves, and if you calculate the group velocity, this is what you get. The group velocity is of the order of about 40% of the mean flow. Okay. Please be careful about this. This is what is called the signal speed. Okay. This was what was defined by Sommerfeld. He wanted to identify the wave propagating disturbance in terms of a signal, and that speed is indicated in this column. And this is the energy propagation speed that would come along when we formally apply the disturbance energy equation in terms of ED. So, these 2 columns let us not worry about, we will go as we go along, we will signify what they are. For the point B, which was at corresponding to omega equal to 0.15, we still have 3 modes, but all 3 of them are stable. The least stable is 0.01. So, that is you can see it is quite significantly damped solution. The group velocity ranges are different, but the leading mode has almost similar group velocity like the unstable modes. The point C corresponds to the one that is far ahead of the neutral loop, and you can see the here the decay rate is decay exponent is even larger compared to the point B. And point D is the one that we chose at 0.05, omega equal to 0.05, which was sitting very close to the neutral curve, and that is what you indicate. You see that the decay exponent for the leading mode is quite small, 0.001, whereas the other mode corresponds to this. Now, if we keep this in mind and try to perform the analysis, we can figure out the various kind of solutions that we get. This is what we are seeing here. If we do that Bromwich contour integral, obtain the phi, and from the phi we do double inverse transform to get psi d, and from psi d I can obtain the V d. So, the V d has a component which is a streamwise component u and a wall normal component v. So, this u is plotted here. So, for the point A, for which the circular frequency was 0.1, the solution is shown here at a significantly large time, t is equal to 801, and what you see is basically this, that you have a local solutions, and so if we do the Bromwich contour integral method study, then we solve the Orson field equation along alpha and omega plane, and we do get the value of phi for those values of alpha and omega. Then we perform this double inverse transform here to get psi of d. Then we take a curl of psi of d to get the disturbance velocity, and the streamwise component is u, that is shown here, point A, for point A, which is which corresponds to omega naught equal to 0.1, shown at a significantly larger time, t equal to 801. Please do understand that in the omega plane we have taken 512 points. So, if I define my omega range from -1 to +1, then what have we got? We have gotten the delta omega. We have the range, we have the number of points, we got delta omega, and from Nyquist limit we can convert it into the corresponding T max. What is the maximum time we can get? And that is what you are seeing here. So, if I take only 512 points, I can go only up to 801, and if I have to take more number of points for a longer time, then I have to take more number of points. So, this is the trade off that you will have to understand. At those times when we were working, this was the limitation of our computer. What we notice is, of course, the local solution followed by asymptotic solution here, and the asymptotic solution is followed by a front which decays, and this is what we would expect, because this is nothing but a wave packet, right. We are studying it as a spatiotemporal entity, and we see that the disturbance at a finite time can only reach up to a finite distance. If I were to take more number of points so that I can go to much larger t, I would perhaps see it would fill up the whole domain, right. So, that is what we do see. So, this is what you see for point A, but however, when you do it for point B, this is how the flow really evolves, and according to our spatial stability analysis, this was a perfectly spatially stable system, and that is what we are seeing. The asymptotic part is strictly decaying. However, at t equal to 450 and at t equal to 801, we do see this wave front, and this wave front actually increases with time, and this is something that was not understood before. Now, you can note that for both these points A and B, we have done the simulation for Reynolds number of 1000, and we do get at the identical time almost a similar wave front. So, the question is whether this spatio-temporal wave front that we are seeing is a function of Reynolds number, or it is due to interaction of multiple modes, is something that is an open question at this point in time even. And this solution that we are showing you here has been obtained for the point at the inner maximum. Inner maximum is about quarter of a delta star that we have seen for this Reynolds number case. Now, that is what we discussed it for the point A. Receptivity solution is dominated by the leading unstable mode without any effect coming from the damped part of the solution, right. We did not see any moderation because we have the solution. So, we could calculate its growth rate, right. We can do it, and we have done that, and that helps us making that last statement that the growth rate matches exactly what is given by the first mode. So, the second and third mode does not give us much in terms of the disturbance flow quantity. If you look for the point B, the asymptotic solution is once again due to the first mode, and the growing wave front, interestingly enough, the alpha r, the wave number of the wave front, matches with that of the second mode. Effect of the third mode is not at all seen for the point B, not in terms of alpha I or alpha r. So, basically this forerunner that we see, it continues to grow spatiotemporally even though the other part, asymptotic part of the solution decays, and this is something interesting that we need to understand. We do make an observation here that the case that we see that the necessary condition for the creation of forerunner is found by looking at the receptivity solution for the points C and D. For point C, we have a single stable mode, and later point D, we have two damped modes. For point C and point D, the solutions look like this. For point C, we do not see any wave front, but please do understand this is at a different Reynolds number. Whereas, for point D, we have two modes, both are damped, but we do see a kind of a spatiotemporal growing wave front. Okay. This is somewhat tempting for one to now conclude as if that a necessary and sufficient condition for this spatiotemporal wave front or the forerunner is that you must have more than one mode, because for C there were only single mode. At the same time, we must also keep the option open of future studies where one should study a similar analysis, do a similar analysis for different Reynolds number cases. Because for point C, although we have a single mode, but this is also done at a very lower Reynolds number. So, this spatio-temporal growing wave front, is this a strong function of RE? So, that when we reduce RE, it decays, or it is due to some kind of interaction of multiple modes. This is something that we need to understand. Okay. So, this is what we observed, that the spatiotemporal front for the case B has a wavelength of B2. Whether this is just a pure coincidence or it is because that mode becomes important is something that has to be furthermore studied in greater detail. However, what we can say or do at this point in time is to note that if I depended solely upon spatial stability analysis, then of course, I would not be able to get the spatiotemporal front. The spatiotemporal front is obtained because we performed a Bromwich contour integral method, because we treated the problem as spatiotemporal problem. Okay. So, that is something that we must and we must further probe at multimodal solutions of Reynolds number with Reynolds number, and then try to see what is the propagation property of this spatiotemporal wavefront. This is a major outstanding problem that needs to be really studied. Now, next what we want to study that okay, supposedly that spatiotemporal wavefront is a attribute of a function of RE, and multiple modes are not so important. Let us say we grant that, but then we want to study a case where RE is of course greater than RE critical, and then we will consider the response of the system where circular frequency has a bandwidth, and in this bandwidth all the frequencies are unstable. And then what will happen? Because of the way we write it, they will mutually interfere, and now this interference is both in alpha and omega plane, and this is what we need to study. Let us try to find out what happens. Now, although we make this observation, but we would keep our options open. However, we just simply mention that the growth of the forerunner is due to probably this multiple modes interacting with each other, and they probably add to the phase. You know, this is what is the concept of groups, and this has been going on from the time of Hamilton, Rayleigh, and so on and so forth, all the way up to the nice monograph by Brillouin. And we talk about the properties of forerunner, which was studied by Brillouin for electrodynamics problem. The propagation speed of the signal has been variously defined by group velocity, which we adopt in our case, signal velocity by Sommerfeld, and energy transfer velocity by Brillouin. Brillouin noted that the three definitions are identical if we are looking at non-dissipative system, but here of course our study involves dissipative system because we are looking at viscous flow. So, this does not hold. What was noted by Brillouin that for electromagnetic waves, this forerunner is very weak in case of stable system. Only it can attain high values when the group velocity is minimum, something probably related to what people later on called as absolute instability. In dissipative systems, these three velocities that we talked about, the group velocity, signal velocity, energy propagation, can be different, because we can have both stable and unstable modes existing side by side. So, that is what one can do. Group velocity we can obtain as we do here and shown in the table, obtained directly from eigenvalue analysis. And if I look at the signal itself, if I plot psi versus d or u versus d, x, then I can calculate. Let us say the point of maximum, at what speed does it go. That is what we call as the signal speed, and estimation of energy propagation speed actually would require that we study this energy propagation equation itself, and this is what we study next. To do that, to develop an equation for ED for this particular case, we can define the disturbance energy also in terms of its Fourier Laplace transform. Okay. So, E of d with a cap is a strong function of y, height over the wall, and also as a function of alpha and omega, and which will perform the Bromwich contour integral to get the quantity in the physical space. What is the governing equation for this? Well, governing equation for this is here, given in the physical plane. So, now we can substitute our representation for psi d Vm Ed like this and write it down here. Now, you can very clearly see what is this quantity. This is your del square Ed, right. If I take a y derivative twice, then I will get this E d cap double prime, that is your second derivative with respect to y, and this is your second derivative with respect to x, minus I alpha whole square will give you plus I alpha whole square will give you minus alpha square. And these all these terms that we see on the right hand side, we can open them up, and suppose we have obtained those quantities from the Orson field equation. That is what we have done. So, we can write it down here, and you can notice that the quantities that determine the energy propagation is dependent on u velocity, the shear, the curvature of the velocity profile, as well as the third derivative. So, this is something interesting, because if you recall that when we looked at Orson field equation, we saw the Orson field equation depended on the mean flow from the definition of u and u double prime. But here, when we are looking at the disturbance energy, it not only depends on the mean flow, but it also depends on the shear and the curvature and the third derivative of the mean flow. So, this is something interesting. Now, this equation that we have just now seen, we can solve it again along Bromwich contour in alpha and omega plane. Okay. Now, once we have gotten that E hat of d as a function of alpha and omega for this Bromwich contour, we can do inverse transform and obtain the solution, and I am showing you the solution for that point A and B in that figure. A corresponds to the unstable point, B corresponds to the stable point, and this is what you get. Well, of course, for the point B, you do have from the Orson field equation, it is spatially stable. That is what you are seeing here also. Please do understand that when it comes to this equation, can we do a stability analysis? See, this comes strictly from the Laplacian, and we cannot do the stability analysis like what we did for Orson field equation, right. This is interesting, because there is in this equation, if you look at, there is this is the forcing term. So, this is not like your eigenvalue problem. There is explicit forcing coming in from here. And if you look at the so called transfer function here, transfer function does not involve any term related to the mean flow. So, stability of what we are studying? See, this is something you must understand, that this is a very, very interesting alternative viewpoint, whereas in the Orson field equation, the governing equation was homogeneous. Here, the governing equation is inhomogeneous. In the Orson field equation, we had a transfer function which was a function of the mean flow. Here, we have a transfer function which does not depend on the mean flow. Right. So, this is something that is interesting. So, when we study E of d by this Bromwich contour integral method, it is a very, very interesting thing, because what we are looking at here is nothing but a forced vibration problem. Forced. What is the forcing? That is coming from how the mean shear interacts with the disturbance shear. That gives rise to this kind of thing. And despite all that, of course, it is excited by the forcing. So, whatever may be the forcing property is, that is seen here also. For example, point B was stable. So, we do get asymptotically stable energy. However, we do pick up the spatiotemporal growing wave front, and for the point A, which was right inside the neutral curve, we do have a growing wave front, and there is this leading wave front present in both of them. These are shown for Reynolds number of 1000 at a height of 0.278. Okay. So, this is what we need to study. So, we can make the following observation, that the variation that we are seeing E of d versus x, this variation is much smoother than u versus x. Well, we would expect it because it is squared, right, v squared term. So, if I have some discontinuity in v, when I square it, it will smooth out. Once again, for the point A, there is no detached forerunner, while the point B display the same detached forerunner as before. The rate at which this wavefront propagates, we can work it out from the figure itself, and this was obtained in table 1 as V e. Recall, we talked about V e. What Brillouin suggested, that we should also talk about energy propagation speed. So, since we have now got energy as a function of x and t, we can calculate the speed, and that is how it was obtained, and it was noted in the table. That the system dynamics is determined by the least stable mode A 1 for the spatially unstable case, with all the 3 definitions of propagation speed producing identical results. That is what we saw. So, I think I will stop here. So, tomorrow's next class, we will be talking about what happens to this. Then we will make a kind of a grand summary of whatever we have done so far. We have been focusing mostly about spatial growth. We will like to see what happens in flows where we instead have temporal growth. That will be our next stop in our journey.